engineers from Air Worldwide to give a guest lecture. So you have been learning statistics for the one semester, and so this one we just want to some people who use them in the real world and give you a little bit flavor what kind of applications you can do. Okay, yeah. So Air Worldwide. I guess Cassie is going to give more introductions. They were a company mostly working on disaster modeling. So let's use a lot of probability and statistics in addition to all kind of scientific knowledges. Okay. So I will give Ram first give an introduction. Okay.
So my name is Ram Nagupalli. I work for AI Worldwide. I've been with AI Worldwide for 3 years. With me today to talk about the work that we do and how it applies to what you're learning in the classroom is Dr. Kiran Chennai from the company. He is a researcher in the modeling team. So he's going to talk about modeling work and the application of the learning that you're doing in this class, how it directly applies to what we do, and even beyond that. So you can give you a flavor of what goes into building catastrophe models. So I'll talk about our company first, and then Dr. Kiran will introduce you to the concepts behind modeling for the catastrophe industry, catastrophe modeling industry. And then we have also with us Andrew Rahibi. He's just here to observe us talk and give us a peek afterwards, I think. And he worked with me in the quality assurance department. And the other speaker today is Dr. Igor Sisel. And he's a colleague of mine in the quality assurance department. He's a recent PhD graduate from Boston University, and he's been with the AIR for about 9 months. So he graduated just a year ago, exactly, right? Tomorrow is a year ago, tomorrow is the event. So he can give you a good perspective on how he has migrated from being a PhD student in applied mathematics, systems engineering, and his modeling experience and his graduate work, and how that's translated into working for AIR. And I also have with us Cassie Romachal. She is in our human resources department. She's a manager there, and she has a business card here in case some of you are graduating or thinking about AIR, our sister companies at Veris, which is our parent company. We have a lot of sister companies that are part of Veris, and if you're interested in employment opportunities, she's good. She can talk to her after the class. Okay, so let's get started. So AIR Worldwide, it's not AIR, it's AIR. AIR stands is an acronym, and it's Applied Insurance Research, what we use the name. We'll call it AIR Worldwide because we model for catastrophes worldwide. Right? So I can figure this out. Okay. So as I said, AIR is part of, how many of you know actually what AIR does? Many of you looked up what AIR does? Okay, so let me give you an introduction of AIR, and then I'll dive into the company and our corporate structure. So AIR is, as I said, applied insurance research. So what we do is build the models we model catastrophes, whether it's natural or man-made catastrophe. So, for example, we have models for hurricanes, severe thunderstorms, winter storms, flood, and that's one of the topics that Dr. Kiran is going to cover today. And floods happen, how floods happen, how do we model them. And the reason we do all these models is not for studying why these happen or how these happen, not just that, but really to help the insurance industry estimate the kind of damage that buildings or insured properties will sustain. And that way they can estimate the losses by how much they have to pay out people who insure with them. So the idea behind what we do is really not only science and engineering, but also there is a big financial component involved in building these models. So not only do we have the physical models, we also have the financial models to help insurance companies negotiate through their business arrangements. So AIR has I'll give you a little bit of a history. AIR's parent company is called Verisk Analytics. It's based in New Jersey. And Verisk is a holding company. It's a publicly traded company. Its market cap is around anywhere between $11 to $12 billion. And these are all the family of companies that are part of Verisk Analytics. As the name indicates, Verisk, we basically are in the business of risk analytics. When you talk about insurance at the most base level is nothing but a risk transfer transaction. So we have Verisk family of companies are associated with helping insurance companies in different sectors, like health insurance, property insurance, life insurance, all of these different fields of insurance, the sectors of the insurance market are serviced by Verisk family of companies. AIR is one of the bigger parts of Verisk. So a brief history of AIR. It was founded in 1987. We are the first company to model catastrophes. We're a leader in this business. As you can see, we've been around for a while. And so we have offices. We are headquartered in Boston, just in Back Bay. And then we have offices in Europe, Asia, and we're always expanding, obviously. Within the U.S., we have an office here in Boston as well as in San Francisco. Okay? So we have, as it talks about, we have about 400 clients worldwide. As I said, we're part of the Verisk Insurance Solutions Group and over in Boston. So this slide kind of gives you an idea of what the insurance marketplace looks like. Okay, so whenever either you want to buy a house or a car or anything, for example. And by the way, AIR services what is called as the property and casualty segment of the insurance market. It's up here. There's health insurance, life insurance, there's liability insurance, and other specialty types of insurance. AIR is really in the market of insuring physical property. So what does that mean is that whenever you want to buy an insurance, you can either go to a retail broker or you can go directly to an insurance company. And then the broker might go to an insurer who insures these policies. So once the policies are, the insurer might need to get additional coverage. Because insurance is a highly regulated business, every government wants to make sure that whenever a catastrophe happens, insure a building, something happens to this building, the insurance company has to be able to pay off. So what happens typically is that governments regulate the way insurance policies are written, insurance rates are set. So what happens is that insurance companies are limited by how much insurance they can write. So in order for insurance companies to write more policies, what they do is they go to what are called as reinsurers. Reinsurers, we don't hear much about reinsurance, but reinsurers are really the backbone of this industry because they support or they insure the insurer. So without the insurer, the insurance market will be pretty limited. Without insurance, business cannot run because if this building is not insured, you can't actually step into this building, or this building can't be operational. So insurance really is a lifeline for business. So what happens typically within the insurance food chain is that whenever an owner of a building buys an insurance, there's a lot of players that are involved. So the insurers, as I said, the retail brokers, and there are insurers, and there are insurance brokers, and there are the actual reinsurers. Now the question comes up is, where do the reinsurers go to generate the money to cover for the policies that they pick up? So what they do is that they will in turn go into the stock market and float what are called insurance-linked securities. So there's called the ILS bonds, or sometimes they're called the catastrophe bonds. So these, again, what happens with these bonds is that they're picked up by capital markets. So, for example, if you're employed and your employer has a pension policy, pension fund, they collect all your pensions for your 401ks or your mutual funds. Those people, again, in turn, invest in these catastrophe bonds. So who owns those bonds, those mutual funds? We own them. So again, the people who have the building, people who own the property, are also the people who end up buying these bonds that are put out by the reinsurance company. So this is really a full cycle, or a full chain. So that we're actually, on the one hand, we're paying for insurance, we're also investing in these bonds and other secure forms of security. So we invest in big insurance companies by either buying their stock or through the bonds through our mutual funds and others. So as you can understand, this is a very complex as well as the full circle chain of tiers of market. So now to talk about a little bit of the history of the catastrophe industry. So as we said, we started in 1987, and we started modeling the U.S. hurricane, tornado, earthquake models. So these were introduced in the late 80s, 87, 89. And if you look at the evolution of this market over the years up until 2012, is that the models came up. In the beginning, the adoption or the use of these models was limited because people really didn't understand. It was a new field. But then in 1992 and 94, we had Hurricane Andrew, which had about $16 billion in losses. And then the Northeast earthquake in California, we had about $12 billion in losses. So these were huge losses for those days in the early 1990s. So people suddenly realized that in order for them to manage their portfolios of insurance policies, they really need to model and understand the risk associated with writing these policies, underwriting these policies. So there were a lot of insolvencies as a result of Andrew, about 11 of them. When we talk about insolvencies, we're talking about big, huge insurance companies. So what that meant is that the government had to step in, or if it was not properly regulated, that means that the insurance policy holders probably suffered in not able to recover from the losses. Then again, in 1997, they introduced the first earthquake model for Europe. So we were limited to the US during the early 90s, and as the market took off, we started to write our first, we wrote our first earthquake model for Europe in 1997, and then the first bond was issued in the mid-90s. So again, as the demand for these insurance policies and the coverage and the losses started mounting, there were other capital that was needed to be brought in. So the capital markets got involved, and though they started, looking at how do we analyze the portfolio, how do we manage our risk, right? So that's how it kind of started to evolve. And then we had our first World Trade Center attack in the early 2000s. So then, people started looking at modeling terrorism. This is man-made risk. When we talk about hurricanes and earthquakes, those are all natural catastrophes. Now we're talking about man-made risk, right? So we started to build catastrophe models. We started looking into them. And then we had, the hurricane season with Katrina, 2004, 2005, huge losses of $41 million. That's a tremendous, eye-opener for the industry. We had 3 insolvencies as a result of Katrina. Even though we learned in the early 90s that, this is a big problem and that people need to manage their risk better, we still ended up having, because of the scale, the sheer scale of the losses associated with Katrina. So that kind of gives you an idea of, now when we look at 2013, we release a new product with, modern interface, very scalable architecture. So now we're looking at making these products that we're providing for the insurance industry to be more sophisticated. So how do we put our software together, right? So when we talk about Touchstone, our products, so we have the models that we build, but then the models are, the science, the engineering, and the finance part. But then we also build products that are targeted towards these different markets, segments. So we talked about insurers, we talked about reinsurers, and we talked about bond writers. So we have specialty products that are built for all these different users of these models. So when we talk about our product, the product basically consists of the contracts of the risks, the risks that are insuring. So we call them exposures. So if you're talking about this building, this could be part of that portfolio of policies that an insurance company writes, and that could be categorized as an exposure or an exposure to risk. And then we also have, descriptions of the hazards as well as the vulnerabilities, the drivers of uncertainty, the enterprise loss potential. So all of these things are elements of the model that we call as the catastrophe model. Now for this, we collect a lot of data from different sources. And this data is analyzed and put together in a way that can be disseminated and used down the line when we model. So not only do we use the same data that we collect, our customers also depend upon huge amounts of data that we collect. For example, information about how this building is constructed, what type of construction it is, where it is located, what kind of soil does it sit on, so that we understand that when a catastrophe happens, then we can accurately predict what kind of loss, the physical loss the building will sustain, and then from that, we can actually calculate the financial losses. So in terms of the company itself and the people that work at AIR, so we have people, we have about, as I told you, we have about 500 people in the company at AIR, plus growing obviously now, probably approaching 600. Right? So, and about 80 to 100 people have own PhD degrees in various fields, from engineering to atmospheric science to systems engineering, applied mathematics, and and financial fields also. Now these are, as I said, we have engineers, we have seismologists, we have geologists, we have applied mathematicians, we have physicists, we have software specialists, and statisticians. So some of you, in the future, maybe you'll be employees of AI as you master your statistics field. So from a software point of view, how do we build our software? What is our software foundation? So in terms of our software, we develop software using C#, .NET, which is the Microsoft set of tools. We also use C++. Obviously, we need to manage the data. We also need databases. So we use SQL Server from Microsoft, and we're also now exploring what we call the big data technologies, and the company called Aptian, which produces a product called itself. So those technologies are also used in putting together our products. From a software testing point of view, which is of interest to me, I work in the quality assurance department. We do different types of testing. We use agile methodologies in developing software. One of the things that we need from a software point of view is strong statistics background. So we look for people that have a modeling experience as well as statistics experience, exposure to, obviously, some of the quality assurance tools like Selenium as well as SQL. So this is kind of gives you an idea of how we build the software. So we analyze the requirement from our users. So since we've been here in the industry for about 20 years, so we have, as I said, we have 400 different clients. So while we are building new models and new catastrophe models, so while we're building new models, we're also updating the current models that we have. Every year, we get new science that tells us that we need to update our models to make them more precise. We also get new data, so there's always new construction, there's shifts, there's new cities that are being built, new types of construction that are coming to play. Governments enforce new structural codes or new building standards, so we have to update all that data also. So what happens is that we get a lot of input from our users as well as new science that happens. So what we do is that building our models, we take into account all that stuff. When we build software tools, we're also getting feedback from our customers. They're in the different market segments, whether they're reinsurers or insurers. So what we do is we take that feedback, we design the programs, we write the code, document and test it, and then we release it to our customer base. Any questions?
Does AI have techniques for modeling social phenomena, such as, for example, social movements? Say in the Middle East, when said movements became known, would AIR have techniques for reevaluating insurance policies for concerned parties there?
Can you repeat the question?
Okay, sorry.
Speak up a little louder.
Okay. In short, does AIR have techniques for modeling social phenomena?
Like example?
Like a social movement in the Middle East, for example, people.
Okay, so I think I get the question, if I understood the question. So let me give you an example which is parallel but not exactly the same. So one of the man-made catastrophes that we've gotten into modeling is pandemic flu. Okay. So the spread of pandemic flu. So there are parallels to it, it's not exactly the same. Okay, how do the pandemic flu start? It starts from one single source, right? So it spreads due to different environment conditions, travel, the type of disease it is, and all of those things, right? So we do model something like that. Now we don't really get into the social movements. Okay, we do model terrorism. Now we have a sister company called Maplecroft, which actually monitors terrorism risk of where hotspots are. So they are looking at social, political, other types of risks, and they develop some scores. I think right? They do write risk scores. So terrorism risk scores. So if there are hotspots, they're monitoring them. So there are companies within the Verisk family that are doing some of that work, but unless there is a demand for it from the insurance industry, we don't really venture it. So one of the hot fields right now, as all of you know, is cyber risk. So there's a huge amount of financial losses that companies can sustain. So companies are looking to get cover for cyber risk. So for example, recently we had Target being hit or Sony being hit by a cyber crime, right? So what happens there is that companies need to protect themselves from liability. So they are looking for ways to model cyber risk. So that's an area that we're actively working. How do we assess cyber risk? What are the elements of that risk? What are the different things that we need to look at in order to accurately model and give tools for the insurance industry to assess and manage that risk? So we're constantly looking for new areas, but I don't think we've done the social. Do you agree? Yeah. Is there anything else you want to add?
No, I think you covered it well, but there was some talk whenever the pandemic, going back to the pandemic risk we were talking about, there was some ideas about following the social media to say if there was a correlation in how it was spreading, and that just because of how the media was, or even Facebook, for example, was reacting to it, is there a correlation? Can we use that information to predict how the risk is spreading? Google came out and said, even before the Ebola, for example, the previous one, even before some of the aid workers could think about, or the people who were involved think about where it was spreading, social media was giving more information about how it was spreading. So it's an interesting idea.
You have a question?
Yeah, so when you collect new data, you have like feedbacks all the time on your model. When do you actually decide like, oh, my model is not good enough, it needs to be improved, or like you say this is probably like statistical noise and it's probably good enough? Like when you get feedbacks, like you have a bad year, for example.
Exactly.
How do you single it out compared to like?
That's a great question. We don't, just because a data was available there or your model performed badly at a particular scale, it's not a reason for updating, but we do tend to look at how the data is available throughout your domain of interest. And every few years we do come up with an update or kind of change some of the things in the model. And also in that time there could be a new methodology or a new modeling approach that could result in a better or accurate measure of your risk. So we adopt that, and every few years we update the model. But it's not just one case where your model is behaving badly. Because we go with, I don't know if Box was a big statistician, Box, and then they said all models are bad, but some are useful. So we go with that approach. You know, as you drill into your model, if you start looking in a very detail, there are a lot of parameters or variables that can be wrong. But as information becomes, our approaches improve, we update our model every few days.
You didn't understand fundamentally that all these catastrophes are random events. They're very unpredictable. There is no, exact science to model them. So at the end of the day, our model is only as good as the variables that we put into it. Now that comes with a cost. More the variables, more compute. So you have to kind of play the devil's advocate. To some extent, you have to say, okay, what are the most important ones? And a lot of the times, what we do with our models is we calibrate against the field data. So insurance companies collect a lot of claims data. So whenever a claim is filed, whenever Katrina happened, right, they collected a lot of data on damage as well as payouts. So we calibrate our models against actual live data. So real data that comes out of this insurance. So we're always calibrating our models to make sure that as we learn more, our models get more precise. So as we have more granular information, we can get more and more precise in our prediction.
Like a small, let's say like a big event, like one of those, like for example, like the Japanese earthquake would happen like once every like couple hundred years or something like that. Like that wouldn't change your model that much because you calibrate it so it's robust enough.
True, but Tohoku, you're talking about Tohoku earthquake. So there were a few things that was new that are the church, what's the Christchurch. Sorry, thanks. That nobody thought there could be an earthquake in Christchurch, but it happened. So that was a reason for going back to our model and say, oh, there was a fault there. So if there was a thing in the next release of that model, we'll try to incorporate that information and release it. But just because you will not, it's not easy to go back and change something and release it next year. So it takes some more study and research that goes into that.
Any other questions? Before we get into the next more interesting segment.
Thanks.
Anything else? Anybody else? Any questions? Here. That is close up. Here to talk about the math and science and the engineering behind catastrophe modeling is Dr. Kiran.
Thank you, Ram. My name is Kiran Chinnakanalli. I'm one of the many people who work in the flood model. I'm the hydrologist of the team, or one of the hydrologists in the team. So our team is about 20 people. 15 of us are in Boston, some are in San Francisco, some are in India office in Hyderabad. In the course of the next few slides, what I want to kind of show or demonstrate is the different expertise that you need to put a flood model together. So we have meteorologists who look at the precipitation, hydrologists like me who look at how that precipitation is transformed to flow, and there are hydraulics engineers, data analysts, GIS specialists who look at and prepare GIS data for us. What I want to do is just go through the history of how we have developed this model, but just to give you a flavor of the different flood products that AIR makes. But I would like to get into the modeling itself. So we'll present in a cartoonish view of what a flood model for catastrophic industry look like. Then we'll get into the details of overall picture of how the flood model is put together. Then we'll again, since it is a statistics class, I'll give you some examples of different applications that are within the flood model. So please feel free to interrupt and ask questions if something is not very clear. Ram was mentioning all the different catastrophic model EIR has been producing, and this is just a picture for the flood model. You see that relative to what Ram was saying, the first model from EIR came out in 2008. That's relatively recent. One of the reasons is flood is one of the most complex perils to model. Also, there are two different model products here. One is given at the bottom. These are what we call fully probabilistic model. It's much more comprehensive way of quantifying flood risk. While on the top one, you just see it's a hazard map. These are flood products, but it's just you have risk maps. You can think about risk map, binary maps. You can say your exposure or your building is in your floodplain or outside it. I'll talk a little bit about that. But the idea is, one is what we do. When we say a flood model, we are developing this flood model for the entire nation where there's a need, where there's a market, or somebody asks us to say, okay, we want to estimate the flood risk in this entire country. So developing a model for the entire nation is pretty challenging. I'll show you some of the characteristics of the flood model itself that makes it very data intensive. And since then we have been producing these models, but we are also learning, we are also improving the methodologies, and I'll talk about some of them in the next episode. So just to step back and say, okay, what is a flood model? What does a flood model for catastrophic industry should comprise of? The reason I'm doing this is also to give some vocabulary so that we are all on the same page to understand what are we talking about. So let's think about this nation of 3 houses. This is the entire country. There's just one river in this nation. But this is an advanced nation. They collect all kind of data, precipitation data. It's very, very well measured, and they also have a stream gauging station. This is how generally the flow data from your rivers are collected. So I say this is a fantasy country because it also has data going back to 10,000 years, let's say 10,000 years, so they've been collecting data. And we make some assumption that nothing has changed, no climate change, land use has pretty much been the same, and only 3 houses remain. So I call this a fantasy land because being a flood model, if you have 10,000 years of flow, precipitation data and everything, that's awesome. That I would say, oh wow, this is where I want to develop my flood model. So what you do is, think about, let's say because of this is a pretty advanced nation, it's also collecting all this data. So it said, okay, on year 1 there was this flood, this kind of flooded these kind of houses. It went all the way up to whatever house. And for every event they have catalog. So this is what, let's call the entire record as a catalog. This is what we are interested in developing. So based on the flow information for that gauge, so you have been collecting, every year you collect what was the highest flow that happened. So you can determine what was the flow that happens every 10 years. What is the magnitude of the flow with a frequency of 10 years. And you can delineate the extent of that. For example, something like that. So it says every 10 years the flow happens, this gets flooded, and it goes up to this one. Similarly, because of 10,000 years, you can also say 100 years extent would look like that. What USGS in US has done is it has constructed these maps, something like your 10-year zone, which is in the red line, or the green here, which is the 100-year line. These are what the FEMA terms as the high flood frequency zones, and everything outside is also of different frequencies. So what I'm getting at is, in order to create those create those extents, you need a lot of data that goes into your model. And using your catalog, somebody can say how many times your particular exposure got flooded in that entire record. So since we have this catalog, and we also have the catalog of what happened every time there was a flood, what was the extent of your destruction for each one of these exposure points. So based on that, you can relate whenever a flood of this magnitude happened, there was this damage and a particular exposure in a particular location damaged 30%. that is what they call the damage functions, which relate the intensity to the damage of a particular exposure. Using that, you can construct what we call the exceedance probability curve. So what I'm showing there on that is on your x-axis is the return period and the y-axis is the loss. And you can construct this kind of curve for just one exposure or for the entire nation or for a particular state, etc. But the idea is, given the return period, you have an occurrence loss. Just one event, what was the event that caused, and what are the return periods of that. Or for the aggregate, for the entire year, there were multiple flood events and multiple damages happened. So there could be a total damage for every year, and that could be the return period. So the idea of the catastrophe model is, if we can construct this 10,000 year catalog and combine it with the damage functions, and then if you package that in your software and give it to the insurance or the reinsurance companies, they can put their exposure on it and study how these curves look like. And based on dicing and slicing into different regions, they can discriminate what is a risky region for them to write flood risk or not. So that is the whole idea of flood model for catastrophe. Now let's go back and come to the real world, where we do not have these 10,000 years of observations. What do you do? So that is the question. So how do you develop a model with all the possible occurrences of floods in your entire nation so that you can construct this flood model? So we base our model on simulation. Simulation itself can be of different kinds. It can be a statistical simulation where you are drawing your events from particular distribution or particular joint distribution. In our case, we believe in modeling flood based on physics. What that means is you start with your hydrological cycle, break them into three different components, which is precipitation. How do you model precipitation? If you use that to create runoff and flow in your landscape, and how do you then model your flood extent? So there are basically three components to your physically based flood model. Just to give an example of the flood model, what is the underlying net look like? For our US flood model, we use a 30-meter digital terrain model. This is the elevation for every 30-meter grid cell for the entire landscape. Based out of that, we created multiple events of precipitation, board precipitation in your computer world or in a simulation world, and using the physics that drive this precipitation into runoff, we created this catalog. So just to give you an example in terms of the resolution, this 30-meter DTM will result in over 15 billion grid cell points in the nation. So for example, your TV with the high definition TV has only about 9 million points. So it's one extra magnitude of higher resolution. So that's the concept of it. Now let's get into a little more meat. So how do we put this model together? EIR uses this framework across different perils, no matter what peril it is, either hurricane modeling, earthquake, or in our case, flood. You start with the hazard model. So where the idea is you're going to simulate multiple different events to create this 10K catalog or 10,000 year catalog. For every event, you also have to simulate its temporal and spatial signature along with the magnitude. So if you create this 10K catalog, you can then use the exposure information, that is all your buildings and different types of structures, and estimate your damage. And you can put your policy conditions, the prevailing policy conditions, and then estimate your insured losses. But for today's talk, I'm only going to be talking about the hazard model. So, and we will get into some of the details of the hazard models, starting with the precipitation. Modeling precipitation is very important because that is the input to your flood. That will control how your flood patterns flow. So we start with what we call the global circulation model. So anybody have heard that terminology before here? So global circulation model is something people use to study climate. If there's a climate change kind of a thing, they try to simulate the entire atmosphere using this global circulation model on the left side. It's a very coarse model. Every grid cell is about 300 kilometers by 300 kilometers. Then you use that information to run your regional physics-based model, which is the numerical weather prediction model. Numerical prediction model is something your weather man will tell you, or weather channel is using to say what is the weather for the next few weeks. It's a regional scale. The physics is better resolved than the global model. And then on top of it, you use a statistical downscaling method to further increase the resolution of this precipitation. So what we are doing is, going from left to right, we are increasing the resolution of the precipitation, but more importantly, we are capturing the pattern of how the moisture moves at these different scales. So this is important because when you're modeling flood, as I said, you're creating these events. So some stream links in Texas are highly correlated with some links here because of the dominant precipitation pattern in this part of the world. So it's very important we get those patterns at different scales accurately. So moving from precipitation, we simulate this precipitation from sea surface temperature for 10,000 years. So we have created this precipitation catalog. And now we are going to use that precipitation catalog to run your physics-based runoff and flow generation model. So just to give you some idea about how the runoff generation model works, let's think about a small watershed. Anybody know what a watershed is? A watershed is a geographic region which contributes the precipitation that falls on it as flow to the nearest stream. Just to give you an example, this is a small basin in Vermont. If you are a skier, you will recognize this is right next to the Killington ski area. So what I'm calling watershed could be, or unit catchment, is each polygon which consists a stream. You can think about a book, a sliding book, right? If the water falls on it, it's going to first go to the edge of it and then falls over. So this is your unit catchment. And as water falls on each one of them, it's going to go through this river and it comes here, and another tributary contribute, and the water is just going to go out of the basin. So what we call watershed, or the entire basin, is the sum of all these unit small catchments above it. So this would be your entire catchment area. So if there's a precipitation that's falling on it, all streams will contribute, and as it goes down, you have more and more water. So this is what we call the physics-based approach. So just to summarize, we start with 10,000 years of precipitation. We run it through a snow model to say what is falling as snow, what is falling as rain. Then we collect that, run it through a flow generation model, which will account for the saturation of the soil, and if there was a snow melt, etc. And then it will result in the water that gets out of that catchment as the flow versus time. And now we start collecting from different unit catchments to create this hydrograph. Hydrograph is flow versus time, and the flow at any point can then be estimated. So if you think about the precipitation, now you can convert that into flow in a river, and based on where you are in the river network and based on how intense the precipitation was upstream, you'll get very high magnitudes. So then, based on that, we'll also create events. So we are creating, think about that 10,000 year catalog, we are creating that catalog. I'll get back to the event definition if there is any time, but the idea is, based on this, you're dividing this entire thing into different flooding events. So using that flow information, you can now construct your flood extents, which we call hydraulics. Hydraulics is the domain of engineers. They use higher scale or higher resolution of scale. They look at the digital terrain model. They look at how the land surface is changing. Using the flow information from the hydrological model, you can then start propagating the wave in your river channels. and create flood extent maps for each event as shown on the right side. So moving on, using the same methodology, you can create what I was showing as earlier as your 100-year map. Shown on the left side here is such a map for NEC, a part of NEC coming from, sorry. On the right side is the AIR flood map, and we are comparing with the FEMA's 100-year flow map on the left side.
Did you decide which one is better?
So that's a good question. So this is, first of all, this is not a validation because we are comparing two different models out here. So we can be completely off. We both can be completely off, and still we will not know. This is the only to give you a benchmarking way of saying, okay, FEMA had produced this and we have produced this, and if there are any differences, why it is so. So there are differences here. If you look at closely, some of these are, we are probably underestimating the extent here. In some cases, we'll be overestimating the extents because of assumptions that we are using. Assumptions could be different. The data that goes into building these extents could be different. So this kind of comparison, especially with your flood maps, will tell you if the models are different or if they are using the same data, etc. So just to summarize the flood model, before we get into some of the statistical applications within the flood model, we started with the precipitation, 10,000 years of rain. We ran it through the snow model, then the runoff and flow generation model. We get flow for each one of those events. Using that, you route it through your drainage network to estimate flow at each one of your catchment. You can think of this as your entire country, and then you can produce flood extents. So for your entire catalog is now ready. You can use that, put your exposure, define your damage functions, and estimate your losses. So before we go, any questions until now? Okay, I'll keep going. So I started off saying a physically based model. So, and I also said there are differences where there is a statistical simulation approaches or physics-based simulation approaches. Though we say ours is a physics-based approach, there are a lot of these statistical, and I kind of alluded to some of it while I was describing them, that are used. Without statistics, we tend to have limitations in how to develop this data and how to use the model. So I'm going to give some of those examples in the next slide. But before that, let's have a flood-related but a probability model. This was something that I was given when I was taking statistics class as part of civil engineering. So if you have a house that's sitting in a 100-year floodplain, 100-year floodplain is where they say the flood happens once every 100 years, or it's in that zone. Or in more probabilistically, this is the zone where the possibility of annual exceedance probability of your flood is 1%. So given that, if you have a 30-year mortgage, what is the probability that your house will get flooded? What is that? 0.3? Think about it, we'll come back to this. So 30-year mortgage, 100-year floodplain, in that 30-year period, what is the probability that your house gets flooded? Alright, so we'll come back to this problem in the end. So let's talk about some of the applications. So validation, Ram was saying we calibrate and validate our model. So this is the validation example. We start with the gauge data. Gauge data is very important. I also kind of mentioned that the gauge information is there, so you can go back and validate your model. So one such validation we do that is at 100-year flow. On the left side, each one of these points is where you USGS as a gauge. USGS is the US Geological Survey as a gauge sitting on your stream measuring stream flow data. On an average, you have about 30 to 40 years of data on each one of these gauges. But now in the validation, I'm saying the observed 100-year flow versus simulated 100-year flow, and I'm showing a decent comparison between them. So the question is, if you have 30 years on an average on these gauges, how do you estimate a 100-year flow data, 100-year flow on these gauges? Distribution fitting is the answer. So USGS has come up with different distributions that they suggest that we use while using these data. So for a particular gauge, this particular gauge is a very good gauge because you have maybe about 100 points. So for every year, you first pick your maximum that happened in that year. And this is what we call annual maximum series. So if you have 30 years of data, for every year you know what was the maximum flow. Based on that 30 years of data, you fit it to a distribution. In this case, we are fitting it into what USGS suggests as log-Pearson type 3 distribution. Once you fit the distribution, using the distribution, you extend your return period, or you can go advanced. You can say what is the 100-year flow or 200-year flow. Of course, the uncertainty increases as you go further away. But with the 30 or 40 years data, it's easily or it's relatively easy and significant to estimate your 100-year flow for each year. So that is one application. So now the second application is we have around 9,000 gauges that I showed in the previous map. But still, if you think about your watershed here, you might have 3 gauges as shown here. But still you have a lot of other links. For example, in the US model, we have 300,000 links, 300,000 links, and only about 9,000 data. But as a flood modeler, you need information everywhere. How do you transfer the data from the gauge to the ungauged? This is a big challenge for the hydrological researchers across the world. In fact, I think the last decade was named as the PUB decade in the hydrological world. That means prediction in ungauged basins. What are the different ways you can predict hydrological variables in ungauged basins? The answer is, and again, you are trying to say what is the flow or what is the flow characteristics in all these other links where you do not have gauge data. So the answer is what generally is termed regionalization. At the very basic of it, what you do is you take your whatever flow you are looking at, which I'm kind of representing by Q, and you try to predict that as a function of your watershed attributes. So each one of these polygons is a watershed. Watershed attributes, what does that mean is, if you think about the assumption here is the geology, if the climate, if the slopeness or the geomorphologies are similar, then the flow characteristic or the hydrology is similar. So based on that, you try to build a statistical model. Your watershed attributes could be your climate attributes like your precipitation or humidity, things like that. Your geomorphological attributes are how the channels are constructed, or what is what is your geology, or what is your soil type. So based on this, you develop a statistical model to transfer information from gauge to ungauged basins. So that's the second example. And then again, Ram spoke about the calibration. So we use calibration as a tool to get to the model accuracy. So what that means is, we have a real world. We are trying to predict something using a hydrological model, and we try to know. We get the output from the measure. We get the output from the model. Compare them. Based on that, you try to learn and estimate your parameters or tune your parameters to get very close to the reality. So, but it has a lot of challenges. I think I still have about 10 minutes, so I'll stick with that. So the idea is you're tuning your parameters. So how do you estimate these model parameters? And while doing that, how do you estimate your uncertainty? So we are collaborating with a professor at the University of California, Irvine, to use some of his methods. He is as per work. I encourage you to go to his web page. He's a hydrologist, but he has used all of these Bayesian approaches to calibrate model and estimate uncertainties. So he has also he's very good in naming his models like Dream or Amalgam, or he has others, so do check it out. So the idea is, when you're calibrating your model, you have to estimate the uncertainty behind the parameters. That means you have to estimate your posterior distribution of the parameters. It's not just one parameter, but the distribution of the parameter, and the parameter interaction has to be quantified in order to understand the structure and hence improve the structure of the model. So this method, which he calls Dream, lets us do that. Going further with the same approach, he also uses the approximate Bayesian computation. This was generally used for genetics, but here we are trying to learn about the model, try to getting closer to the reality using different parameters or statistics based operations. So I think I'll not get into the details of it, but I encourage you to go to Asper's webpage and read more about it. Just before I end, there are a lot of other examples. I'm only talking about hazard. One was the statistical downscaling I mentioned. Statistical downscaling is more of a mixture of your statistical approaches with signal processing or machine learning approaches, where you need to, when you are increasing the resolution of the precipitation just from the data, you need to account for the scaling or the physics of how the precipitation changes, while you need to understand how the statistics change when the resolution changes. We also use machine learning and clustering algorithms to create our events. If there is flow that's happening in two parts of the country, how do you divide them into different events? How do you identify that they are different events? So some of those approaches are heavily used. So if you have answers to the problem, you can go back to that. It's 26%. So it's a pretty easy calculation. So if you have a 30-year mortgage, first of all, you're saying probability of not flooding in any given year is 1 minus 0.01. It is 1% chance of probability, so it's 0.99. So probability that your house will never get flooded in that 30 years is 0.99 raised to 30, which is 0.74. And the probability that it will get flooded at least once is 1 minus 0.74, 0.26, or 26%. So I think with that, I'll hand it over. This is just a summary of the different skills. I'll hand it over to Igor, unless you have any questions.
Great, thank you. Okay, so before I start, obviously as the title says, using R in core QA, I really hope that you know what R is and that you use it. Not really. I see somebody uses it. Okay, then at least somebody. So yeah, I'm going to talk today about what I do on a day-to-day basis as a core quality assurance engineer at AIR, and I'm going to go through the examples of using R in my everyday work. It's a free statistical programming language, and it has like three main advantages that I really like. First of all, I can read in all of the data of many different data types. Advantage B, I can analyze the data inside of the program. I don't have to use any other software to do statistical analysis, do the plotting, do the geospatial analysis, and so on. And lastly, what's also very nice, especially in industry, is that I can automatically generate reports, which then I can share with my colleagues, with my boss, and across the company chain. And so it's very nice, it's very useful, and since this is statistics class, I would definitely recommend that you check it out. And it's free, what's the best, and it has millions of people use it, so it has a very strong internet Q&A part. So as a core quality assurance engineer at AIR, what do I actually do, or what do I validate? As Kieran was saying, he, as a research team, at the end of the day, they create a model, but what they actually do is create those catalogs that he was mentioning. So basically a catalog, in case of, for example, a 10,000-year catalog, is going to, for every year, is going to have, for every event, it's going to have like one entry in a catalog. And this catalog can be of a different file type. For example, it can be a CSV file, it can be a regular text file, it can be an Excel spreadsheet, or even it can be as a SQL, in a SQL database. So one of the biggest problems that I have when validating those catalogs is that some of the sizes of the catalogs can be huge. So over 50 gigabytes with more than 600 million rows. So you can imagine that having files of that size is even hard to kind of read them in any software, let alone do any analysis on it. But as you will see, using R, I'm actually able to do this. So the objectives of this catalog validation is to perform data validation. So this is different than what Kieran was saying, where he is trying to validate that the model that AIR develops is can be compared to the real data. Here I'm talking about data profiling, so that the data that is in the file, that it's correct, and that all the variables in the file are within certain allowable parameters. I'm checking for data consistency, meaning that usually for each model I will have multiple catalogs of kind of different type. Here I'm going to be talking in particular about an earthquake model. So I can have shake part of the model, I can have a tsunami part of the model. And since tsunami is actually generated by the shake, I'm going to have one event in the shake part of the model, which corresponds to the one in the tsunami. And they have to, basically, all the variables have to match across the files. Then I'm doing logic tests. I'm going to show an example of this. So all of the catalogs, they have a bunch of variables. In case of an earthquake, I'm going to have when the earthquake happened, where it happened, what was the magnitude, a bunch of angles, and so on. So for each of those variables, the variable has to satisfy a certain, let's call it like a logic, which is actually given to me, kind of the tests are given to me from the research team, and so yeah, every variable has to satisfy a certain amount of certain tests. And then lastly, I do distribution tests. So as Kieran was also saying, showing a lot of plots. At the end of the day, I create also a lot of plots because each of the variables has to abide a certain distribution, and then I have to check that those variables in the catalogs actually satisfy this distribution test. I'm going to mention a little bit about the data optimization, what I was doing with this earthquake catalog. So as Kieran was saying, they develop 10,000-year catalog. But in some cases, the research team actually develops, for example, 100,000-year catalog, but the catalog that's actually implemented into the software is going to be a 10,000-year catalog just for the computational efficiency. but we have to make sure that this big catalog, the 100K catalog, and the smaller catalog are statistically optimized version, statistically similar, and geospatially similar. So basically the smaller one has to be statistically and geospatially optimized version of the bigger one. And finally, I'm going to show a little bit of data presentation, because as you can see here, I deal with a bunch of different file types, different sizes, different tests, but at the end of the day, I have to kind of present the data in a meaningful way. So I'm going to show a few examples of how I present my data in terms of like interactive plots, basically representing multidimensional data on 2D plots, which can be very useful to kind of just present data and to find a certain outliers. So I'm going to start with just giving an example of an earthquake ground motion catalog. So this is not actually catalog that AIR develops. This I just took from the USGS website, but you can think of it that it's very, very similar. So for example, this catalog is what we call a historic catalog, because it actually contains the real events that actually happened throughout the history. So one of the columns is going to be year when the event actually happened, month, day, and hour of the event, at which latitude and longitude the event happened, what was the magnitude of that event, and then some other data. In my particular case, when I'm dealing with this earthquake ground motion catalog that AIR created, I have 27 columns and I think around 500,000 entries, 500,000 lines. So it's a basically pretty big matrix. So as I said, my first step when I get this catalog is to perform data validation. So in that step, it's kind of straightforward. I take every column and I calculate what's the minimum value, what's the maximum value, the mean value, how many number of unique values there is in one column, and what type it is. So for example, in the example that I show, year goes from 1900 to 2015. This is the mean value, number of unique values. So this here is basically just done so that we can, sometimes I don't actually know what the columns mean. So by doing this test, I can kind of make an educated guess of what each column represents. If I'm not sure, then I contact research, go back and forth with them until I actually know all the values. But this is also very important because it's very easy to find some obvious outliners in the file. For example, if the year would be 2016, the catalog is developed in 2015, so obviously something would be off. So this is the first step that I actually do, data profiling. Then the next step is doing those, that I said, logic tests. So in the catalog, for example, year has to be non-decreasing. If you go through the catalog, the year has to increase. Then month has to be between 1 and 12, hour 124, magnitude between 5 and 10. Below 5, those earthquakes won't actually generate any loss. If you go above 10, there hasn't been any earthquake with magnitude greater than 10. So here I just named a few of the tests. In some of my examples, I have up to 40 of these tests, and I'm using R to kind of hard code this test so that I can automatically know if the catalog passes or fails the test. So this is the first kind of, for the people who actually use R, like a first package that I would advise. So when you use R, and actually some other programs like MATLAB, I think, you can very often find an error that says cannot allocate a vector of size, something, 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 which means that basically you cannot read in a file of a particular size. The file is just too big. And the reason for that is usually that all this like statistic packages or software that you use actually read in the file into your RAM, into your memory, and if there's a limitation on the memory, just simply cannot read in the whole file. So the first package that I kind of advise is this FF package. It's just called FF or flat file that handles the memory by storing the data on the disk. The way it actually works is it will read in one chunk of the file, store it onto your actual hard drive, delete it from the memory, and then again read in the new chunk, store it into your hard drive, and so until it reads the whole file. And for example, this allows me to read into my software a file that has more than, as I think I said, more than 600 million lines, more than 50 gigabytes of size file. So this is very useful. And also one of the packages that I use in R is RODBC. So R just stands for the software. ODBC is Open Database Connectivity. So this allows me to connect to a SQL database and draw the data from the SQL database into my software.
The
So
SQL database was also have trouble reading 50 gigabytes.
So yeah, that was, we were actually, when I was doing this test, this was on a tsunami intensity file. For example, you can think of, I'm working in South America, so the South America goes like this. It has like a very long coast, and tsunami, in our cases, as Kieran was saying, the resolution goes up to, I think, half a kilometer grids. So, and you have, for every grid, you're going to have the time at which tsunami comes, the velocity of the tsunami, the height. So it's like a huge file, right? And I was trying to read it into a SQL, and you can do it, but then the problem is doing some statistical analysis on it. It basically takes maybe the same amount of time it does in R, but so short answer is you can do it in SQL as well. But I just found R a little bit more responsive and easier to use. But of course, by using this package, without it, I couldn't read it. So as I said, the first part was doing the profiling, then creating this distribution test. I'm going to go directly to the examples. So here, when I have that catalog, I have columns. Each column is one variable. And as I said, the variables kind of very often have to abide to a certain distribution. For example, if you think of an earthquake, it can happen any time in the year. So you're expecting to have, if you have for example, 10,000 catalog with, so 10,000 years, you're going to have, I don't know, around 300,000 events. And when you plot how many events happen within a year, you're basically expecting something uniform because there's no seasonality to earthquake. But if you were to be looking, for example, to a hurricane, then you would expect to have more events during the summer and less during the winter. So this is just like a one test that you can do using just a visual inspection if the profile, if that variable satisfies the distribution or not. Another example is distribution of annual event frequency. So here I'm plotting how many events happen within 1 year and how many such years I have. And this has to be like a bell curve shape, and again, this would be kind of like a pass. Another example is distribution of magnitude. So I'm expecting to have smaller magnitude events, more of them, and less events of higher magnitude. So we should have distribution of bits, and this would always also be a pass. And so all of these plots are generated again in R using this package ggplot2. And what's nice about it, so not only I can do this histograms and distributions, I can also do a lot of geospatial analysis. Here I'm just showing plotting a certain latitude and longitudes on the coast of South America, but you can actually do a lot more. And I'm actually going to show an example of this towards the end when I'm going to talk about a little bit of data presentation.
So the distribution test you just did visually, or did you also automatically do this test?
So in this case, I mean that's a good it would be ideally to have like an automatic yes and no. So here I'm just doing a visual test, but yeah, I think that's very easy to do to test if it passes a certain distribution or not.
I was thinking that this is an introductory session called to talk about some tests like those.
So we do this at least in some of the distribution fitting I was showing.
Yep.
We also throw out these parameters and variables to the goodness of difference.
So as I mentioned, data optimization. So if you remember, I said that very often there are two catalogs, the big one and the small one. The small one that's actually implemented into a software. So this implemented catalog has to be a statistically and geospatially optimized version of the research catalog. So here I'm not going to go too much into details. I'm just kind of showing an example of what I do, what we do. So here the light green one is the bigger catalog, I think. The dark green one is the smaller catalog. And when you plot a lot of data on this plot, you can kind of see that there are some, that it's not like perfect fit. For example, here this is a distribution of magnitude. You can see that I'm having a lot of I have more smaller events in the big catalog than in the small. This is like you can think of it as a probability density function of a focal depth. That's also one of the parameters in the catalog. So there is some discrepancy here. Here I'm just plotting the actual epicenter of the event within the radius of 150 kilometers around this city, Santiago in Chile. So you can see that here I'm actually having events in the big catalog, but they're not showing in the small catalog. And then this was an example of that I already showed the annual frequency. Again, it's not a perfect fit. So I kind of developed this, let's call it a tool that kind of represents all this data, provided it to research, and then the research did the actual optimization of the catalogs. And just the example of before and after, you can see that now it's almost like a perfect fit between the two catalogs, which means that of course this is like locally around only one city. I look at actually 50 cities in South America, but you can kind of say that the smaller catalog is actually statistically and geospatially optimized version of the bigger one. And the last 5 minutes, I'm just going to show you a few examples of what you can actually do with R. So I'm going to introduce two packages. One is R charts, and then later on this eFleet R. So what's very nice here is, as I said, I'm dealing with a lot of data. At the end of the day, I have to just present it in kind of a nice way. And since very often I'm dealing with a multidimensional data, it's nice to have it represented on a 2D plot. In this particular case, I'm showing for every construction and occupancy. In construction, you can think of having a steel building, having a wooden building, and so on. And for occupancies, you can think of it being as a commercial building, residential building, and so on, just to give you an example. And here we have, I think, around 120 different occupancies, and I think 110 different constructions. And then for every of these combinations, when an actual event, an earthquake happens, you're going to have a different loss. The building is going to react differently. So what I'm plotting here is called like mean damage ratio, which is kind of you can just, for simplicity, think of it as the loss that the building actually, happens at the building of a particular combination for that particular event. And hopefully this works. So the nice thing here is that I can actually generate this as a standalone HTML file, and as I said, it can kind of represent multi-dimensional data on a 2D plot. So as I move, it's not only like color-coded, it can tell me the actual values of this like mean damage ratio as I move on this plot. Another example is if I want to go a little bit more into details. So this was also generated using that R-chart package. So here I just represent data a little bit differently. So here again I have occupancy, so just think of it residential, commercial. Here I have loss, and I can turn on and off different constructions. And what this allows me is, I think if I'm correct, 111, 112 are different. They're different wood structures. So I can plot them and see if they kind of behave similarly or differently, or and I can check if there's any discrepancies in data. And I can also again do this mouse over, and then it will actually tell me, for example, for this guy, let's see, that the construction class is Adobe, occupancy class is a healthcare service, commercial, and a particular loss connected to it. So this is very easy to do kind of a debugging to see if there are any discrepancies in data. And then I want to just show for last two slides is using this leaflet R. So that's another package to display spatial data on interactive web maps using JavaScript library called leaflet. Here I gave just like web links if you're gonna check it out. So here what I'm doing is for different resolutions, again I'm plotting what the loss is depending on the geographical region of a country. This is in Ecuador, and color coding the loss. Basically, I'm color coding the loss, and this is also what I call interactive. That I can zoom in, zoom out. I can zoom in, zoom out. I can click a button that will actually tell me where exactly I am, what's my ground up, what's my loss here, and again look for if there are any obvious outliers. And I think I have one more example. So this one takes a little bit longer to load because it's like a higher resolution. Hopefully it will work. I usually look in Chrome. So. Okay, here we go. So this is actually up to 2.5, I think, kilometer resolution. So if you actually zoom in, you will see. You will actually see the points, and each of that points is like one exposure. And then I have an associated loss to it, and I can do this color coding and then look for any discrepancies in the data while validating the model. And I think I'm going to stop here. Yeah, sorry that not a lot of you use R, but hopefully this was useful, and I definitely recommend checking it out. Yeah, if you have any questions, I would like to answer.
course, and yeah, I decided I'm going to use R from there. So yeah, we use SAS this semester. So if you want to, yeah, so if you learn R, then even nowadays it's used in so many places. Okay, yeah, so yeah, let's thank the guest lecturers from the worldwide, and yeah, so it's really nice, and you can see, yeah, as you learn more and how the things we are going to use in the different researches. Okay, yeah. All right, yeah, so questions, you want to talk to the lecturers, so we can.
If anyone has questions about internships or any other potential opportunities, email me. My card's on the table. I'd be happy.
Oh yeah, right. Yeah, so there.
And there's some headphones and things down there.
Yeah, there's some souvenirs you guys can take. Okay, I think.